Good morning.
Hey, good morning. How are you today?
I'm good. How are you?
Not too bad. Not too bad. Just gonna get things ready, and yeah, we'll begin in 10 minutes. And here we go. Okay, so 7 questions. One about reflection and or reflection. One where you're gonna have to find some kind of mirror lens setup. Double slit experiment question. Two that involve the topic of interference within films. A single slit diffraction question and a diffraction grading. All to be done in the span of 2 hours next Friday from 1 to 3. And there'll also be a little bonus question that, again, you don't lose marks for attempting, but it can kind of bump you up. Um, so I have a question here with the apex angle. No, don't worry about prisms. Just kind of the main stuff, right, is just not prisms or anything too complicated, like the full telescope, microscope setup, or interferometry, or anything like that. I'm just kind of looking for the more basic setups, such as single or double mirror lenses, magnification between an image and the object, that kind of stuff. So if you got a good hang of things in the assignment, the assignment does cover everything but the last chapter of optics. So the assignment kind of, you know, is a good example of the kind of questions that I could have probably put any of the assignment questions on the midterm, for example. And I'll also put up some practice too for all this, because after all, the last chapter wasn't part of the assignment. So, I do recommend practicing your single slit and diffraction grading stuff. So it goes without saying, polarization's not part of it. As a matter of fact, for the purposes of timekeeping, polarization is not going to be part of any assessment for this course. You will learn about that later once you delve into electromagnetism. And the bonus question will be, well, the bonus question could be any of these topics. It's a mystery, but provided that you have a good conceptual understanding of them, the bonus question is going to be a bit more conceptual, so that if you get a good grasp of things, then you can score some bonus points. And yeah, on Wednesday, I'll talk a bit more about the midterm. That said, though, I do want to take the time this week to talk about relativity, because your next assignment is going to be pretty much all relativity. It is a long chapter. It is a very, I don't want to say difficult, but it's definitely a very esoteric topic, because we're sort of rethinking the way that we have experienced life, basically. We're now being told that on Earth and on a spaceship, time passes differently. Not every clock in the universe ticks at the same rate. And therefore, our whole understanding of time and even space is sort of shaken by our full understanding of relativity. And that can be quite a sort of mind-blowing moment for us if we think about it too much. But Einstein once said, time is an illusion, a very persistent illusion. So for this chapter, you really have to just give yourself the chance to, think out the situations, the questions, the examples, and really take the time with it, because it's easy to confuse ourselves with what's going on when it comes to relativistic speeds. So really, it's just a matter of taking our time and trying to almost think about it, but not think about it too much, because we can end up confusing ourselves more than anything, especially when you have multiple frames of reference moving at different speeds. So for now, to start things off, I want to show you a video. I put it up in the recording in the lecture slides, but I think it's better if we watch it together, because it's a very important part of the sort of special relativity chapter, which is
it's the idea of the twin paradox. I'm going to let it speak for itself, so I'm just going to go ahead and share the slide here, and I think there's a button to share sound. So I'll let it speak for itself.
On their 20th birthday, identical twin astronauts volunteer for an experiment. Terra will remain on Earth, while Stella will board a spaceship. Stella's ship will travel at 86.6% the speed of light to visit a star that is 10 light years away, then return to Earth at the same speed. As they prepare to part ways, the twins wonder what will happen when they're reunited. Since a light year is exactly the distance light can travel in a year, Stella's journey should take 23 years. But from having studied special relativity, the twins know it's not that simple. First of all, the faster an object moves through space, the slower it moves through time, compared to an unmoving observer. This relationship can be quantified with something called the Lorentz factor, which is defined by this equation. And secondly, the length of a moving object as measured by an observer at rest will contract by the same factor. At 86.6% the speed of light, the Lorentz factor is 2, meaning time will pass twice as slowly aboard the spaceship. Of course, Stella won't notice time slowing down. That's because all time-based processes in the ship will slow down as well. Clocks and electrical devices, Stella's biological activities including her rate of aging and her perception of time itself. The only people who could notice time on the moving spaceship passing slower for Stella would be observers in an inertial or non-accelerating reference frame, like Terra back on Earth. Thus, Terra concludes that when they meet back on Earth, she'll be older than Stella. But that's just one way of looking at things.
Okay, this is a very thing that we tend to get confused in this chapter. When you're moving really, really, really fast, you start to see the effects of time dilation and length contraction, but they don't happen to you. They happen to your surroundings. So you're flying really fast in your spaceship, everything surrounding you outside your spaceship, you see its length contracting, and you see everything seems to slow down. But from your own spaceship, everything is normal. Everything is just as it was. So length contraction and time dilation are observed, but not experienced. Anyhow, moving on.
Because all movement is relative, Stella argues it would be just as valid to say her spaceship will stand still while the rest of the universe, including Terra, moves around her. And in that case, time will pass twice as slowly for Terra, making Stella the older twin in the end. They can't each be older than the other, so which one of them is right? This apparent contradiction is known as the twin paradox, but it's not.
So just to clarify what they're saying here, if you're in your spaceship, the idea is that from your point of view, someone back on Earth, you see that their time on Earth get dilated, and that means that from your point of view, time is going slower on Earth. However, from Earth's point of view, they see your time on the spaceship getting dilated, so things are going slower for you on the spaceship, as seen by someone on Earth. So the idea is that both twins will see each other's time dilate. So from each other's point of view, the other twin is aging more slowly. But it'll explain now why that's not the case.
Not really a paradox, just an example of how special relativity can be easily misunderstood. To test their theories in real time, each of the twins agrees to send a burst of light to the other every time a year has passed for them. Unlike other objects, the speed of light is always constant, regardless of an observer's reference frame. A light burst sent from Earth will be measured at the same speed as a light burst sent from the spaceship, regardless of whether it's on its outbound or return trip. So when one twin observes a burst of light, they're measuring how long it took the other twin to experience a year passing, plus how long it took for the light to travel between them. We can track what's happening on a graph. The x-axis marks distance from Earth, and the y-axis tracks the passage of time. From Terra's perspective, her path will simply be a vertical line, with distance equal to 0 and each tick on the line equivalent to a year as she perceives it. Stella's path will stretch from the same origin to a point 11.5 years in time and 10 light-years in distance from Terra, before converging again at 0 distance and 23 years' time. At her first 1-year mark, Terra will send a pulse of light from Earth towards Stella's spaceship. Since light takes a year to travel 1 light-year, its path will be a 45-degree diagonal line. And because Stella is travelling away from it, by the time the light catches up to her, over 7 total years will have passed for Terra and over 4 for Stella. By the time Stella observes Terra's second burst, she will already be on her return journey. But now, since she's moving towards the source of light, it will take less time to reach her, and she'll observe the bursts more frequently. This means that Stella observes Terra aging slowly for the first half of her journey, but aging rapidly during the return half. Meanwhile for Stella, it seems as though Terra, the destination star, and the whole universe are moving around her. And because of length contraction, Stella observes the distance between them shrinking by a factor of 2. This means each leg of the trip will only take about 6 years from Stella's perspective. When she sends the first signal to Earth, 2 years will have passed for Terra. Stella will send 4 more light bursts during her outbound journey, each one from farther away. By the time Terra observes the first pulse from Stella's inbound journey, over 21 years will have passed for her. For the rest of Stella's return home, Terra receives multiple light bursts each year. Thus, Terra observes Stella aging slowly for about 90% of their 23 years apart, and aging rapidly during the last 10%. This asymmetry accounts for why the paradox isn't really a paradox. Although each twin witnesses time both speeding up and slowing down for the other, Stella sees an even split, while Terra sees Stella aging slowly for most of the time they're apart. This is consistent with each twin's measurement of the space voyage, which takes 23 Earth years, but only 11.5 as experienced aboard the ship. When the twins are reunited, Terra will be 43 years old, while Stella will be 31. Where Stella went wrong was her assumption that she and Terra had equal claim to being inertial observers. To be an inertial observer, one has to maintain a constant speed and direction relative to the rest of the universe. Terra was at rest the entire time, so her velocity was a constant 0. But when Stella changed her direction for the return journey, she entered a different reference frame from the one she'd started in. Terra and Stella now both have a better understanding of how space-time works, and as twins who are 11 years apart in age, they're a perfect example of special relativity. Keep flexing your relativistic.
Okay, so that was a little bit confusing. Okay, so what we're trying to say here is that to measure time dilation or length contraction around you, you have to be an inertial observer. So the twin that remains on Earth, who's not Stella, I forget her name already. Let's call her Terra. Wait, that's actually her name, Terra. Terra is an inertial observer because the whole time she's on Earth. But Stella is not an inertial observer because at some point her spaceship turns around and starts flying back, right? So that requires some acceleration turn around. So overall, she's not an inertial observer. So only Terra can properly measure length contraction and time dilation that she sees on Stella's spaceship. Stella can't do that for Terra because Stella is not in an inertial frame. So because of that, then only Terra's measurement of time dilation on Stella is valid, and it results that time dilation properly occurs, and Stella does age more slowly than Terra, since Stella can't properly observe time dilation on Earth. Anyways, so the twin.
Sir?
Yes.
Yeah, I have a question. Like, can't you say that like Stella, I think, is the one that's not moving, and that like the universe is moving like around her? So then like you could like kind of calculate the time dilation between Stella and Terra because Stella is not moving.
So the thing about that is that imagine that there's a third observer. There's a third observer in space just chilling at a space station. If they're watching with Stella and Terra, they will notice that throughout the whole time, Terra's just sitting there while Stella at some point flies one way, turns around and flies back. So the so even if from Stella's frame, when she does the turning around bit, it looks like the universe around her is turning around, that gets into a frame that's accelerating. So yeah, from her point of view, it looks like the universe is kind of like accelerating around her, turning itself around. But if that's happening, then that's no longer inertial, and you have jumped to some new frame. So you can't like talk about time dilation anymore, because the rules of relativity are about inertial frames. But even if from the spaceship, yes, the universe around you looks like it's accelerating, which means that you're not in an inertial frame. So we can't talk about relativity, special relativity anymore, because we're not inertial.
Thank you.
So in other words, only Terra can, because from Terra's point of view, there's no her frame is not spinning around. There's no acceleration. And what was I gonna say? Yeah, I don't like the fact that it's called a twin paradox, because like the video says, it's not a paradox at all. And the way to properly calculate it then is to consider Stella's trip as two parts. Consider the time dilation that she sees in the first half of the trip as separate from the time dilation that she observes in the second half of the trip when she turns around. You had to break it up into two trips because it's a different frame. Going one way is a different frame than going back towards the Earth. And yeah, this is to be honest with you all, I think when I was like in undergrad learning this for the first time, used to give me a headache. It's the kind of thing you really want to think about a little bit and just kind of digest. But it's very, very interesting example, and again, a good highlight of how time can be experienced differently by different people, therefore implying that time is not linear for everyone, that time really is just its own thing. So for the tutorial today, I do want to get a few little questions done on the earlier parts of the chapter. The big takeaways for now are just the effects of time dilation and length contraction that we observe due to the effects of relativity. The effects of light being constantly in inertial frames leads to observing distances contract and times dilate. So just to kind of summarize those ideas first, there's the idea of time dilation where we observe that when there's things moving relative to us, it appears that whatever's happening in there is happening more slowly. The amount by which time seems to slow down is determined by a gamma factor, which isn't really a factor of significance at all unless things are moving really, really, really fast. Because gamma is only really going to become noticeable if the moving object, moving person is like at least moving at like 1,000,000 kilometers per hour or so. So in the real world, we won't really notice time dilate. The textbook has a good example of how this can be worked out, because basically they show you an astronaut shooting light up and down a mirror. And from the point of view of the astronaut, the light just goes up and down, but it's a moving spaceship. So from the point of view of someone on Earth, the light beam is moving with the spaceship. So the light beam from your point of view on Earth, not only does the light have to travel up and down from the mirror and back to the receiver, but the light is also moving to the right. So from the observer's point of view, light has to travel a longer path. And if we applied classical mechanics, we might be tempted to think that, well, if light is traveling a longer path, then from our point of view, the speed of light would be different because it's traveling the longer path in the same time. And usually classical Newtonian mechanics will agree with you. From your point of view, light is moving more slowly. But it turns out that the speed of light is constant in all frames of reference. So what ends up happening is that you observe everything in the spaceship moving more slowly, so that the path that light travels is in fact longer, but it happens over a longer period of time. So when you calculate the speed of light, you have a longer path traveled by light, but over a longer period of time. So the speed of light still turns out to be a value of c. So both you and the astronaut, from your points of reference, agree that the speed of light is c. And again, this is all a consequence of the fact that the speed of light is the same in all frames. It makes time slow down around you when you're moving fast. So yeah, here it's just kind of talking about the gamma factor, and you see how it dictates how much things dilate or contract, and doesn't really become a factor until like moving at 30% speed of light. And the other consequence is length contraction. When there's fast relativistic speeds, things contract. So a fast moving spaceship to us looks like it's contracting, looks like it's getting squished. From the point of view of the person driving the spaceship, though, it's the universe around them that's moving fast behind them, so they see their surroundings get squished. You'll see a baseball getting squished the faster it moves, only in the direction it's moving, by the way. And if you're at rest relative to the baseball, though, like you're a fly riding the baseball, you'll be fine. You see the baseball as usual, but everything around you in the baseball field will look super squished. So the way they determine that is you need to first realize what the proper length is of an object, of space or whatever. And that's just saying that you're measuring it when you're at rest. So whatever size the baseball has when you're holding it in your hand will be its proper length. And then whatever size it has when it's getting thrown really fast, that will be its contracted length. So the textbook, I think, uses LP for proper length, but I think I used LO in one of my slides, which isn't really, there's no standard notation, but I guess LP might be more clear because P stands for proper. What's I gonna say? I want to say anything else about proper length. I think that's probably enough. So yeah. Yeah, so here's just them talking about what I was saying, how if you're at frame with the meter stick, then you get to measure its proper length. But if you're moving relative to it, you're going to see its length contract. That's all. So things get shorter. Running clocks run slow, they say. And I will also add to that running clocks run slow and they seem a bit shorter. So the muons are a great example of relativity because their lifetime is super short. So they're moving so fast, though, that their internal clock appears dilated to us on Earth. So they get to live around 4 times as long. And so that's enough time for them to reach the ground when they're produced in the atmosphere, right? So muons are a result of cosmic ray showers, and they do manage to reach the ground. From the muons' point of view, though, right, their time is not dilated, but what they see is the space between them and the ground gets contracted. So from their point of view, their life is still short, but they have less distance to travel, so they do make it to the ground. And by the way, there's no true frame here. The muon is just as correct in saying that the distance to the ground is short and its lifetime is like 2 microseconds, and you're equally correct from your point of view on the ground saying that the mountain is, whatever normal height it is, and that its lifetime is, 3 times longer than expected. You're both correct because there's no more correct inertial frame of reference. Everything is relative. So from your point of view, what you see is what you see. And lastly, remember how sound waves could appear shifted in frequency when the source and the observer are moving away or towards them? The same thing happens with light waves. So if you're moving towards the source of light, the frequency increases. This makes the wavelength of light shorter, which would make colored light turn kind of blue. If you're moving away from the source, it looks more red, which means the frequency is dropping. And so that's called a redshift. We figured out that the universe is expanding by realizing that light from galaxies is redder than it should be, meaning that everything around us is moving away. It's pretty cool. So basically, the whole field of cosmology actually takes advantage of relativity to understand where the universe was at the beginning and where it is now. Anyways, let's do some questions. So some little questions here to get our feet into the big vast pool of relativity. Let's talk about time dilation first. Let's have Rowan Atkinson here, also known as Mr. Bean, driving his fancy sports car, and he's driving by Big Ben, and he's driving at like 60% speed of light because he doesn't care about traffic laws. And for a 1 second interval that passes on Big Ben, what will Mr. Bean measure from his point of view in his sports car driving really fast? I'll give you a second to think about that. But in these types of questions, I always think about what's the proper time here, right? Because we're talking about time dilation, and time dilation relates the proper time to the time that's being observed. I think the textbook uses TO for proper time or TP. I tend to use tau for proper time just to really distinguish the two. But remember that to keep proper time, you have to be at rest with the clock. You have to be at rest with whatever you're keeping an eye on. So Okay, well. So let me ask, if you're standing on the ground and you're watching the hand on Big Ben that counts seconds, and 1 second has passed, so 1 second interval has passed, are you measuring the proper time?
Yes.
Yeah, because you're at rest with Big Ben. Big Ben's not moving, neither are you. So the 1 second interval, that would be the proper time. Now, if you're in your sports car driving really fast, from your point of view, Big Ben is moving. From your point of view in your car, you're not the one who's moving. It's a whole street around you that's moving. So Big Ben's moving, which means that you cannot keep proper time on Big Ben, because to keep proper time, you have to be still with a thing you're keeping time off. In other words, what you see in your surroundings is the time of all your surroundings dilate. Around you, all of London seems to be slowing down, including Big Ben. By how much? Well, that's what the time dilation formula tells you. And so what you observe from your car is delta t, the dilated time. To figure that out, though, you need to know what gamma is. And I know the formula for gamma is a bit kind of a mouthful. It's 1 over the square root of 1 minus b squared over c squared. That's why a lot of the time the textbook's going to give you the speed here, the speed of the frame of the car in terms of a fraction of c. It makes the formula a bit easier, because that way, if I'm just plugging it in right now, right, I'm just it comes down to 0.6 c squared over c squared, but having c on the top and bottom makes it a lot easier to calculate. You don't have to plug in the speed of light at all then. And then times delta t being 1 second being this. So in your calculator, you're probably just gonna be doing, this formula quite a lot. You can probably save it as a function or something. And yeah, if we plug it in for a car moving at, 60% the speed of light, that's a gamma factor of 1.25. So that means that the time measured on Big Ben is 1.25. In other words, when you're driving your big car, it looks like it takes Big Ben 1.25 seconds for the seconds hand to move by 1 second. In other words, time seems to have slowed down by 20% in the streets of London. Okay, another example here. So Mr. Bean keeps driving around. He turns the corner, keeps driving, and there's just somebody just standing on the street, and they start like keeping time, and they tell Mr. Bean on his fancy car that 1 second has passed. For the driver, though, so let's say that the driver and the observer in the street start their watch at the same time. When the observer on the street shows that 1 second has passed on his watch, the question is how much time has passed on the driver's watch?
Wouldn't it be the same thing as the last question?
Exactly. Yep. Because it's not just Big Ben, it's everywhere around you that time slows down by 20%. So it actually takes 20%. So time's being slowed down by 20%. It takes more time for a second to pass. For you to observe a second passing in your surroundings actually takes more than a second. So you're right. The proper time for the person's watch is 1 second, but you're observing from a moving frame. So you realize that you can't measure their proper time. You can only measure a dilated time, which, yeah, it's exactly. And the wild thing is that from the person on the street, from their point of view, it's actually the person in the car who looks slow. Anyways, let's do a little kind of twin paradox like question here. We have a 30-year-old woman who takes a trip in a rocket, and behind she leaves her 20-year-old brother on Earth. She's traveling at 80% speed of light and it's gone for 20 years as measured on Earth. So when she returns, how many years older or younger is she than her brother? So maybe I'll just talk about this one, but we always have to figure out what proper time or proper length is in these questions. And in this case, we can't trust the woman to keep proper time because she's doing a trip and back, so she's not in an inertial frame. Her brother, though, is in an inertial frame, so we can trust his timekeeping. However, though, he's not keeping proper time on his sister because his sister is moving. So what he measures is actually a dilated time, right? He kind of measures what he thinks, what he has, the time that he has experienced passing. But in his point of view, time is ticking slowly inside his sister's ship. So she's aging more slowly. She has aged less than 20 years because she's moving so fast. In other words, the 20-year interval that he measures is a bigger interval than what passes inside the ship. To figure out the time interval passing inside the ship, well, that's the proper time of the ship, which is also the proper time that it passes for his sister. So we have to figure out gamma then, which again is based on the speed of light. It's a function of speed of light, right? So, sorry, it's a function of the speed of the relative speed. So, in this case, you're probably going to get something like 1 minus 0.8 squared. That should give you a factor of 1.67.
Sir?
Yeah.
Like, why is the proper time on the ship and not with the brother that's not moving?
Because the brother that's not moving is trying to keep, is measuring, with his watch how long it took the ship to leave and come back. And on his watch, it took the ship 20 years to take off and come back to Earth. But that is not proper time. Watching a ship fly off, you cannot keep proper time of that, because to keep proper time, you have to be in the same frame as what you're watching. So only if you're on the ship or you're moving at the same speed as the ship can you keep proper time off it. If you're not doing that, if you're just watching the ship, then you're not keeping proper time.
So then how does a twin paradox work if the twin on Earth can't see the twin in space? But like, how does the person on Earth for like a twin paradox have a proper time on the twin in space?
So you don't, again, so yeah, if you're on Earth, you don't measure the proper time, you measure the dilated time. But you can figure out what the proper time was because you can figure out the Lorentz factor of the ship's speed, and basically that determines by how much time was dilated. So if you have measured how long it took for the ship to come back, and you know by how much time was being dilated, then you can figure out the ship's proper time from that.
Okay. Okay.
So yeah, in the case of the twin paradox, it's true that you can't see your twin's ship flying off into space, but you can keep track of how long it took for the ship to fly off and come back, right? You just mark your calendar, and when they come back, you check the date. So you know how much time has passed for you, but you know for a fact that that cannot be the same time it has passed for the ship, because you can only keep proper time of things on Earth because you're also on Earth at rest with everything else on Earth. For the ship, you're not keeping proper time, you're just keeping time. And so there is a time dilation effect going on. And to figure out the actual time for the ship, you have to account for time dilation. Therefore, what you were measuring was a dilated time of 20 years. For you, 20 years have passed, but not for the ship, because you were not able to keep proper time on the ship because the ship was moving away from you. In other words, to get the proper time of the ship, then you have to reverse engineer the time dilation formula and get that the time you measure divided by the gamma factor is the proper time on the ship. Because again, you were not on the ship, you were on Earth. It took 20 years for the trip to finish. So if you take your time divided by gamma, would tell you that the proper time on the ship was 12 years. In other words, well, it took 20 years from the time that your sister took off and came back. 20 years have passed for you. But inside the ship, only 12 years have passed. From your sister's point of view, only 12 years have passed. So you got to live 8 years more than your sister. However, the brother was 20 years old at the beginning. So at the end of the journey, 20 years have passed. So the brother is now 40 years old. And the sister was 30 when she took off. And from her point of view, only 12 years have passed when she comes back. So, she's 42 years old. So she's still 2 years older than her brother. Okay. So how much time do I have? Just gonna check the time, because I know we get kind of like kicked out. Okay, I still have some more time. Oh. Okay. So, next question. Okay, so there's such a thing as a meter stick projector that launches meter sticks at 90% the speed of light. And if you're just sitting in your chair, just watching this meter stick projector shoot meter sticks, how long will the meter stick be? In other words, from your point of view, you're watching a meter stick fly really fast. So maybe I'll give you a sec to figure that out, but remember that when things fly really fast, you can't measure them properly. So what you get to measure is L. And we know it's a meter stick, so we know that normally So in this case, we know the speed of light, so gamma kind of becomes, it's 1 over, normally gamma is equal to 1 over square root, but now gamma is in the denominator, so it really just becomes a square root on the top. And the gamma factor now, it's like, we know it's 0.9 c squared. So if you plug this in, obviously you expect that the length is contracting, so the answer should be less than 1 meter. It should be about 0.44 meters. So at 90% the speed of light, the length of things seems to contract by half. The meter stick will look half as long.
Sir,
Yep.
how does the 1 over square root become a multiplication factor?
Oh, because normally gamma is 1 over square root, right? So that means that 1 over gamma would just be a multiplication. And that's what we have in the length contraction formula. We have 1 over gamma, right? So just gonna put this in here. Okay. So yeah, so that's your double check, right? Whenever you calculate the contracted length, you should expect the answer that's less than the proper length. Okay, so you're an astronaut and you're traveling at 90% speed of light. You're holding a meter stick. What's the length of the meter stick? I'll give you 10 seconds to think about this question.
And they wouldn't be the same.
Ah, yeah. You gave it
Like
away.
1 meter.
Yeah, you gave it away. I said 10 seconds to think about it and you gave it away. Yes, you're holding the meter stick, so you get to measure its proper length. Therefore, to you, it looks like it's 1 meter. If you let go of it and you start flying away, then yeah, it's gonna look contracted, but not if you're holding it. Okay. So well, there's a lot of time left, but it's a good question to end up. I'll just talk about it. So, okay, big spaceship is passing from another galaxy, and it travels from the sun to the Earth. And for us, we see that if we start our timer, the moment we see the spaceship start approaching us from the sun, we start our watch. And once it gets to the Earth, our watch says that about 625 seconds have passed. So from the point of view of somebody who was on the spaceship, though, the question is, how long did it take for them to reach the Earth? And what was the distance from their point of view? So from their point of view, it takes them less time to reach the Earth, right? So we can't keep proper time on the ship. What we see is a dilated time. So we expect that the time that the scientists measured is less. It takes less time for them. Also, because they're traveling really fast, the Earth-Sun distance is less than what we measure. We're just, at rest with respect to the Earth and the Sun, pretty much. So we see this distance, but if you're on the ship flying fast, the distance should be less. In other words, the time it takes for them to get to us is less, and so is the distance they have to travel. It's like the muon. So what's the travel distance that they see? Well, for us, we see a proper length of the Earth-Sun distance being 1.5 times 10 to the 11 meters. And we know that the distance that they measure should be contracted. From their point of view, they're moving so fast that the space between the Earth and the Sun is contracted. So we know this should be less than the proper length. The time it takes for them to travel should also be less than what we recorded on our watch, because for us, their time is actually dilated. We see their clocks running slower than they actually are from their point of view. So it takes less than 625 seconds. In other words, we do not have proper time on them. We only have observed time, which means that the proper time is obviously less than what we observed, because we observed sort of a dilation of their clocks. And so the proper time must be less than 625 seconds. And when you look at all the options, there's only one option where the time it takes for the people in the spaceship to get to us is less than what we observed. So that will be option A. Okay. And nobody say this one out loud again. I'll give you like 10 seconds to think about it. But copyright-free, lawyer-friendly version of Captain Kirk, some guy called Captain Jerk, reports to headquarters from the USN Enterprise that he's leaving Senesca about he took off 1,000 seconds or so earlier, and HQ is like, are you telling this to us? Is this spaceship proper time? So if it's spaceship proper time, what does that mean? And again, I want you to say this out loud, give everyone a chance to think about it, but think of which of the 5 answers is the proper description here. So if you're leaning towards option B, you are correct, because it's asking us, what is meant by spaceship proper time, and to keep proper time with a spaceship, then that means that you're looking at a clock, you're measuring time while at rest with a spaceship. In other words, on the same frame as the spaceship. So any clock inside the spaceship will measure proper time. If you were keeping track of things back on Senesca, then you run the risk of actually measuring a dilated time on the spaceship. Okay. So this question here sets off, we have another captain here, and he's sending off 2 light signals. He presses the light signal button on his steering wheel, and they flash light at the front of the ship and another light at the back of the ship, and it kind of happens at the same time. So it's kind of like the blinkers on a car, where the car starts blinking on all corners. And General K is watching from a space station, and from her point of view, she's seeing the light from both sides start to flash at the same time. So the question is, what about Captain Ray, who is in the ship, and what does he see with respect to the timing of the lights? I'll let you think about that one. Well, I'll draw a picture of it. So Here we have Captain Ray moving to the right. Flying off where no man has gone before. And yeah, so Captain Ray kind of shoots off, sends off these light signals. And if you're standing, well, if you're just standing on the ground, you're standing at rest. So that, in this case, in this question, is General K, who's just kind of hanging out here. What K sees is that basically the light from both sides kind of travel the same distance because she's right in the middle of the two lights. So the light travels the same distance. For Ray, however, though, he's actually approaching the whole spaceship is moving to the right. So he's approaching the right light while he's moving away from the left light here. So light from this side is going to reach him first because he's moving towards it, while light from the back side is going to reach him later because he's kind of moving away from it. So from his point of view, he's seeing the flash on the right first, and he's seeing the flash on the left, while K is seeing both flashes at the same time. So this would be option B here. He sees the front light first at the bow first, and then he sees light from the rear. Anyways, we're gonna get kicked out in 1 minute. So we'll talk about more of relativity on Friday. We'll include momentum and energy. I put up solutions for the third assignment this Friday so that you can, have a clear picture of what it's all about. I'll put up practice questions as well, and then next Wednesday we'll do some practice. Yeah, you too. Have a good day. Remember, it'll be 7 questions plus a bonus. And yeah, I wish you all a good day, and we'll see you on Friday. All right, everyone. Take care.
Thank you, sir. Have a good day.
You too.
Thank you.
Yeah, you're welcome. All right.